and Zhejiang University in China and Johnson University in Sweden. And we have a strong collaboration with the Coimbatore Institute of Technology, BSc Tech, and Madurai Commerce University, and even Madras University in Chennai. And also, he has a collaboration with Untitled University in UK. His main research focus is on material characterization, especially using advanced electron microscopy. He completed his PhD from University of Berlin in Norway. His prime focus in his PhD research period was about phase transformation and chemical modification on nanocarbon particles. He obtained his bachelor's degree with specialization of a master's degree with specialization in material science from BSc College of Technology. He has very good research experience. He had an research experience at Indira Gandhi Atomic Research Center, Kalpakkam, as well as in Indian Institute of Science during his master's studies. So far, he has published 73 peer-reviewed articles, high standard publications including Nature, American Chemical Society, Royal Chemical Society, Elsevier and Signature on research topics including carbon nanotubes, two-dimensional
I think we lost the connection there. Surinder sir, are you here? Hello, Surinder sir.
Vijay sir, we can.
Yeah, I thought there was problem with the connection. I don't know. Should I wait for him? ஹலோ சார், லைன்ல இருக்கோம். நான் யாரோட வாய்ஸும் கேட்கலையே, பண்ணலாமா?
ஹலோ,
ஓகே, லைவ் ஸ்ட்ரீம்ல இருக்கு. ஸ்கிரீன் தெரியுது இல்லையா? Yeah, okay. So Nias is here. I will talk. Okay. Yeah. So Nias sir, screen தெரியுதானே?
No.
Have shared my
PPT வரல விஜய்.
I will restart again.
உங்க சைடு நீங்க ஆபரேட் பண்ண ட்ரை பண்ணுங்க.
Yeah, I'm trying again. Just a minute. இப்ப தெரியுதா? ஓகேவா? நீங்க சார் ஓகேவா இருக்கீங்களா?
Clear. Go ahead, please.
Yeah, okay. Good afternoon to all. Hope everyone is hearing and sharing. I have shared my screen, so everyone must be visible to us, yes, right? Or clear with the view. Okay, ma? Yes. And thanks for inviting me. I really thankful to Sacred Heart College. There are good friends from Sacred Heart College microbiology biochemistry department, including Dr. Nias. Thanks again for inviting me now with the Sacred Heart College. Yeah, we are connecting through webinar. Of course, it's like new technological driven academic things nowadays due to the corona outbreak. Hope everyone is safe and doing good and safe at home. I wish we recover soon. So with this today's presentation, I would like to share certain things like in how the international research environment goes on with more interdisciplinary in nature in all the departments. I cannot frame this to any single department. It's more or less as I am working more in international. Of course, it's now 4 different universities, including in Norway, China, and Sweden now. So we are working very closely, but more interdisciplinary. So I say very closely because we are working take a particular research questions, broad interdisciplinary nature. We include every point of research aspects, like include different technological things, include different simulations, include different applications. So in that way, we are having more opportunity to work in an international environment covering most of the departments, I can say. In Chalmers, we are working in Department of Chemistry and Chemical Engineering, mostly with corrosion nowadays within the department. But our group is more specific to renewable energy industry and energy policy, I can say. So we are working more closely with metallurgical industries and energy industries and the corrosion research groups of around Sweden and within Europe. So now we have wide opportunities to work in Europe because of the EU policies opened up. So we don't have any restriction to work within the specific limit of boundary or geography. So we have very open environment nowadays in Europe. We have EU framework which gives possibilities, funding opportunities, and even more opportunity to use all the laboratories without any restriction, no matter where you are working and where you are aligning. So we are opening up all the traditional boundaries or orthodox boundaries in the sense, I can say. So that's why I chosen these topics. So understanding interdisciplinary and international approaches. With this, I just pick few lines. I don't want to take a very broad line. I want to pick very few lines to introduce what are the interdisciplinary works going on around the world. So it's like just a eye opener to all the researchers and professors. I see there are many young professors are here, and of course I see very senior professors. Really thankful for you, senior professors, joining here with this for a useful communication here. So with this, I will keep on moving to my slides. So as we speak interdisciplinary, we know from the beginning or from our approach of Indian universities, if you take physics, yes, we have broad opportunity in working in nuclear engineer as a biophysicist or aerospace or high science school teacher or even a ballistic expert, astronomer, or research physicist, or even the material scientist like me. When coming back to chemistry major, yeah, there is again possibility as a material scientist or research chemist or biochemist or microbiology or medical lab technicians, environmental consultant in nuclear engineer. So these are the traditional science subject what we are dealing, and of course in past few tens of years we have also introduced biochemistry, It's again it's a link between the biology and chemistry. Even the physicians are working now in biochemistry, major research, pharmacist, and food scientist, so on. So in Sweden, we have another area including biochemistry, but extending to biophysics. There are more biophysics department in almost all the universities. I'm not sure whether we have in Indian universities if this new courses or new department is introduced at least. Most probably there are maybe a way to go, but still must be introduced as quick as possible, I can recommend. So in Stockholm University, there's a department of biochemistry and biophysics, where they have even courses, which is, I just picked few interesting courses that are suited for my background. For example, the physics of biomedical microscopy. I'm an electron microscopist working in material science, but as an electron microscopy, I have broad opportunity to work in most biological materials or medical things or biomaterials, including nanoparticles towards the bio applications like that. So I picked this syllabus, which is more relevant to me, and it's more interdisciplinary in nature. With this syllabus, they introduce optics, which is, I can say, more related to what 10th, 11th, and 12th physics book deal with in our syllabus, even in CBSE or state board. There are very good optical lessons, introduced microscopy. Even this biomedical microscopy syllabus carry over that one, in addition to in the little advanced one like fluorescence microscopy or Raman microscopy, such things. So biomedical microscopy within the biophysics deals with all the optics lessons. So this is one way of dealing interdisciplinary, and another one, experimental methods in molecular bio, where they are dealing with more material characterization. As a material scientist or material researcher, I can almost all these characterization tools we are nowadays using in all type of material, irrespective of whether metal or biomolecules or physical things or chemical things. And we are also entering into X-ray crystallography toward introducing towards the biomolecules or molecular things. So these are the characterization things which are introduced for all the bio applications, including electromagnetic radiation behavior or thermodynamic nature of biomolecules, how it behaves in that, and all these things. So this is another interesting subject which is introduced within biophysics. And even quantum biology, it deals with more quantum mechanical things of bioparticles. It covers the electronic spectra of photosynthetic complexes. It also covers femtosecond spectroscopy, which is very like fast way of approaching the material and getting the signals detected within few microseconds or femtoseconds, I can say, through laser. So these are the new spectroscopies which is introduced, and more particularly towards studying the biological particles, and they are studying the quantum nature of these biological particles or cells, I can say, in more stressful way. They also have studied the photosynthetic energy transfer between the molecules in different environment. So this quantum biology, it's link physics, more related to quantum physics and biology. It's a combined one, which is in University of Gothenburg, where I'm living in, but I'm working in Chalmers University of Technology. The University of Gothenburg is for arts and science. We are for engineering university. And there is another subject which I came across, which is the rapid biophysical characterization and NMR spectroscopy, structural analysis of small proteins from bacteria and archaea. This is a research paper published in University of Gothenburg. My good friend, whom I share my office, of course, we share same corridor for University of Gothenburg and Chalmers University for certain research people for some practical reasons. So we know what they are working, at least when we are discussing. So that's why I just want to bring it to you. They used NMR spectroscopy to get more research answers from bacteria and archaea through spectroscopy, and they used bioinformatic tools. Sometimes they are also trying to use the deep learning and like machine learning or artificial intelligence in the next sector to bring computer or integrate computer knowledge or computer related terminologies into this biophysics to get in more and more advanced and very quick results, gathering many as much as possible informations. So this is another fantastic work going on in this biophysics field. And there is X-ray crystallography experiments, which at least I used for material science or metals or nanoparticles. But really, I was surprised to see this such a research paper which used X-ray crystallography towards biophysics laboratory or biophysics group, where they studied more lipid cubic phases within some micro-sized crystals and protein structures. So this is another work recently developing, integrating all the material characterization tools towards biological things. That's why it's termed as biophysics, I guess. So this is another maybe future oriented. I don't know if everyone or all the nations are completely into this era now, but it's a needed and it may be the oriented aspect which cover artificial intelligence and machine learning, which gets all the data and integrated data and gives quick reply or answers towards any type of diseases or any type of need for a health or affected people, medically affected people, I can say. So it's maybe developed or it's maybe on the way to get into the future research group into the commercialized or into the people normal use. Maybe it's coming on the way. At least in this type of corona outbreak, we see the data were collected through the mobile phones, like in China, or I heard about those things were also covered in Korea and Taiwan. They get all the data and they have some chips or something is introduced to them, so they monitor all the temperature variations or all the health related issues can be monitored from home to hospital without you physically going there. It maybe it's on the way. Yeah. So the next one is medical physics, which is another well-known department or well-known research group within Indian universities. There are more medical physics applications we are now started to use in most hospitals, even though I'm not sure whether it is there are more open area in research field, but at least in the commercial field, it is, of course, it's derived through the route. Like in medical physics, we can say it's X-ray is a well-known terminology which used in medical physics, and there is imaging like from X-ray, computer tomography, or MRI, MRA, or PET scan, which is more related to physics, but application towards the medical. So this image, which shows what's the need of medical physics, or what are the development which comes across medical physics in this modern era, starting from X-ray to PET scan, like from the 2-dimensional approach to the 3-dimensional approach. MRI use the magnetic resonance imaging, like some unstable atomic nuclei always have produce radio frequency signals. These signals are observed and monitored or detected and imaged, processed later on in MRI. And MRA uses some contrast mapping liquids. It's like MRI, but MRA will give more imaging towards the vessels and veins. PET scan, which comes under nuclear medicine category, where the positron is used, like the radioactive tracer element is injected. Maybe fluorine 18 is used nowadays. I don't know, other chemicals are used in India, but at least I'm sure fluorine 18 is used. That's more commercially usable. So those radioactive substance which goes into the target cells, which may emit positron because of the unstable ligand, then those positron, which is actually an anti-electron, combined with electron from the neighboring cells, then gamma rays is emitted again. So those gamma rays were detected through the 180-degree rotatable detector in all the directions. So it gives 3D mapping or 3D imaging. So this is another example for combining physics and medical, like an interdisciplinary but more commercialized, well-known research, I can say. Then there is a new area which is developing with hadron therapy, or we can say proton therapy. That's anything, because the proton therapy introduced only proton, and hadron therapy, which is a common terminology for proton and carbon ion beams. As you know, the proton consists of up and down quarks. The hadrons are made up of a few, two or more quarks. So these hadrons are used instead of X-rays at some point for the cancer therapy. I don't know, by using the particle accelerator. I'm not sure whether it's already been used in India. But in America, there are more medical universities are using this, if I am not wrong, as I come across some research articles. So this is like advantages which shows than X-rays. For example, X-rays can penetrate deep, bypassing or crossing even the affected tissues. But in hadron therapy, the target cells can be easily calculated, the distance between the source and cells. Then the energy can be varied. The best thing in hadron therapy is it have, for example, maybe the Bragg peak. Means if you calculate the Bragg peak where this particle or hadron have most energy, usually towards the target cells, because of this most intense energy only in this target cells when compared to the distance it comes from the source towards the target cells, it only shows a peak energy or intense energy at some point. That's a Bragg peak, where and where these hadrons spend their energy and die. So it won't exceed, or it won't exceed the target cells than or going into the normal cells and affect those regions as like in X-rays. So this is one of the very good advantages, or the best one compared to X-ray, you can say. These are used for tumor target therapies, radiology department nowadays. Even this images show how the X-rays are penetrating, or how the proton beam can be stopped here within the target cells in all the directions, either it is inside or from the top, or here proton beam and X-rays are behaving. So this is a proton radiation therapy, which is coming into effect soon or commercialized soon. Then I go to the material science. So far I was like giving some perception or like few points from the biophysics and medical physics. And the material science is my subject. As a material scientist, I feel always happy because I have wide opportunity to work in interdisciplinary nature. For example, even from my master's, if I compare certain results or my experience where I was working, it shows how broad is how interdisciplinary is the material science. When I was working in China, I was working in School of Material Science and Engineering. In Material Science and Engineering school, we have 600 students, like 400 from the bachelor, 200 from masters, and nearly 150 PhD students. So it's like different separate college for material science alone. Unfortunately, or like, I don't know why it was, but when I was studying in PhD College of Technology, we have just 10 to 15 people per year always. And after PhD College of Technology is linked to Anna University in past 20 years, it's step by step it was reduced, and the material science course was taken out for some reason, I don't know. But the world have more material science department to bring in all the field experts like in bio or materials or metallurgy, or even the nanomaterial experts to to grow to grow the system in interdisciplinary nature to feed everyone, to feed everything in the advanced world. So the material science is one of the best interdisciplinary course which I at least I am admired towards it, because of course it's personal connection because I am from material science. So it's always. So when I compare my lifestyle, how I use this material science knowledge in different field of uh, platforms. For example, I have worked in physics, chemistry, and engineering. I did my PhD in physics. Now I am working in chemistry. Of course, as it is in energy industry, it is more related to engineering, like metallurgical things we are dealing with. These things is possible because of the interdisciplinary course. Even when I was giving lecture in Chennai, Soka Ikeda College, I see there are students studying physics and computer applications. Really, they were afraid whether it's useful in future because they are the BSc physics with computer applications. Then I said, yes, of course, the world is interdisciplinary, and you have a lot of opportunity for entering into the bioinformatics group or into the computer-related programming. For example, few of my students whom I know, they are working with the electromagnetic theory. They are getting results derived through for Python or MATLAB or C++ or Java. So there are wide opportunities to use both physics and computer applications. And nowadays the bioinformatics groups are developing, and deep learning, machine learning things are developed. So really you have good opportunity, but just you need to drive towards that without any hesitation, or you need to learn more and more. Don't stop over at any point just because of the mark. That's what I used to comment them or commented. So as a material scientist, again coming back, I have such wide opportunity. I will show a few examples where I have encountered different field of research questions and different platforms where I was working. Uh, I was working in Indira Gandhi Research Center as a project student, where I was working in fuel reprocessing plant research. We used the fuel reprocessing plant. There are more corrosion issues coming in, so we were developing a material where the scientists are developing the material. We were, as an assistant, we were working with them. We learned a lot how to use different materials in this reprocessing plant to get rid of corrosions. We learn nuclear physics, we learn corrosion chemistry, and of course, we learn a lot through our Indian scientists in Indira Gandhi Atomic Research Center. This is one of slide which I want to show because it combines all the things: physics, chemistry, and materials. And next, I was moving on to Hyundai Vacuum, where we developed this fingerprint coating for forensic department. I was working with vacuum science. I was in this project. We were developing this one for Ireland forensic department. They need fingerprint coating, for example, where the chemical, like routine fingerprint detection was not possible in some plastics or some other items, like in shoes. There may be some problem. So they need to develop some fingerprint coating. So we used gold and zinc coater. This is, I don't know which one is my hand or this, because took before 14 years. So even I just put my hand and get coated through gold and zinc. So we know the gold is getting coated over all the surfaces, irrespective of ridges and like tops and downs. The zinc, it's one usually sits in the ridges, so it gives contrast mapping, like negative staining, like ups and downs with black and white. So that's why it's easily detectable. It works irrespective of nature. So when regular routine fingerprint detection is failure, these type of machines can be helpful. And of course, you need physics knowledge. This one, like in a vacuum science, then you know why we are using, like, so nowadays they are using zinc oxide instead of zinc and gold. Someone using silver nanoparticles for coating here after zinc coating to get enhancement of color. So these are the things which used nowadays. Then I move on to nanocarbon production, where I was concentrating more on nanocarbon towards energy applications. But the company which I was associated while I was doing PhD, they synthesis nanocarbon from methane. So the methane extraction, then the methane pyrolysis, where we get carbon and hydrogen. The hydrogen can be used in future towards electricity applications, even in chemical industry to produce ammonia, and carbon industry again to wide classified area of researchers. I'm more stick to carbon in my future slides. So these are the another option where the material scientist can work. So coming to nano and interdisciplinary field. So far we are studying about or talking about the field which we are well known, or with the departments well known, like biochemistry, biophysics, and material science. Of course, we are using nano in all the departments nowadays. Either it is microbiology or biochemistry or material science, we are using nano. So the nano itself is an interdisciplinary field. We need to develop more nano related courses in future, nano related departments. I see there are few universities offering nanotechnology from the integrated courses, like from BSc to combining MSc, like a 5-year course, and there are nanotechnology courses in even engineering and technology colleges. It's very good thing, but we need to develop more and more towards application driven researchers instead of theoretical things. So as a nanoscience, I just want to give a few just over it. Like nanoscience is study of structures and materials on the scale of nanometers. Okay, yeah. So the nanotechnology is a technology involving the design, production, characterization, and applications of nanostructured materials. Because the nanotechnology again can be a broad in interdisciplinary nature, can be applicable towards medicine, biology, even in agriculture or industry or environmental things. For example, one of my friends was working with titanium carbide, two-dimensional material, but they are used for environmental applications. Even the carbon nanotubes have more agriculture and environmental applications. Carbon nanotubes have medicine and biological applications. Of course, again, carbon nanotube can be used in industrial applications where the transistor can be developed, or molybdenum disulfide two-dimensional, a single layer with a single catalyst elements introduced or single dopant element introduced, can be used in there are more purification routines like in oil industries. So the development of nanotechnology with low dimensional materials have wide possibility because of the quantum field or quantum confinement effect, which we'll see a few examples over in the next slides. This is one example how this nanomaterials used in different field of applications. For example, if you see this is a DNA nanowire which is created and used as a computing device as well as scaffolds to generate highly organized and complex superstructures through self-assembly. The carbon nanotubes can be used in wide applications. We will see a few examples later on. Of course, carbon nanotubes and graphene as the highest mechanical strength, enormous intrinsic mobility, and zero effective mass, and an electron can travel for micrometers evading scattering at room temperature. So the D is metal catalyst nanowires can be used to connect two chips by growing them in shape of vertical bridges. So then the molecular switching, then the oxygen depleted titanium dioxide memory stress. So nowadays these oxygen depleted titanium dioxide memory stress are also used in neuromorphing technologies. They are integrating biological applications to it, or bioinformatics knowledge deriving or using these things. And there are some nano antennas and nanoscale carbon nanotube radios. Of course, in carbon nanotube, I can say even we are, or like industries, electron microscopy industries are trying to use nanowires and carbon nanotubes as an electron source instead of a traditional tungsten and lanthanum borate filaments. So they are trying to use these nanotypes to get more and more electron beam with more intense nature. So these slides just I want to bring in to show how these nanoscale devices are useful in different applications. So yeah, of course. Now, as I told you, these nanoscience are now combined with machine learning, like getting experimental design and materials from the nanoscience knowledge and integrating into machine knowledge to derive more quick results, and like maybe combining with artificial intelligence neural networks for biological applications and in optical experiments, like in our electron microscope, we are also trying to incorporate this machine knowledge, machine learning knowledge to get more, derive more and more insight knowledge to fix the electron beam or electron pathways within the well-controlled environment. So our groups are even working with this, combining optics, and I have heard biological people are using this one. So machine learning or the computer related things are incorporating into all physics, chemistry, and biological in future. This is one example I want to show you. For example, this is just because of I am from the electron microscopy background, and these are the imaging. So these image sets can be data processed by using machine learning. Then with a defined algorithm, the image output can be enhanced to get more insight. I'll show you one example slide, which is a traditional way of getting blood tissues or thyroid gland tissues through conventional microscopes. This is the malaria infected human blood. There are iSmart software introduced to the optical column to get enhanced results. And in next stage, there are also some algorithm or computer programming is introduced to get more insight into these cells or blood cells to get more results or more informations. So within optical imaging, like as I am related to here, I am showing this example. So within optical imaging, we are also using such algorithms. Nowadays, the Python is completely interlinked even towards electron microscopy to get more image processing data. This example, this slide is towards optical image. Of course, we have good slides from electron microscopy, which I cannot show you because of restriction. So that's why I just brought another optical microscope image comparing how the optics and algorithm is used. Now we'll go to the carbon nanotubes as an interdisciplinary example. The carbon nanotubes, as you know, is an allotropes of carbon. These are the cylindrical carbon molecules, which like a single graphene layer is folded in a single layer or in a double or multi-layer to bring into carbon nanotube structure. Yes. So carbon nanotubes, if I take only biomedical applications, it can be used in a therapy, like in a drug delivery system, or like in a tissue engineering, or in biomimetic implants, then thermal and photodynamic therapy. Like coming back to my field of imaging alone, I restrict here my talk towards the imaging. I will just show a few examples how these carbon nanotubes are used in biological imaging purposes using like fluorescence microscopy or in Raman microscopy. So I'm more closely working with carbon nanotubes in my PhD, where we are used to functionalize a lot. The functionalization of carbon nanotube itself or carbon nanostructure itself is a different, like a broad research area, because it's more like with different functionalized elements or functionalized compounds, you can introduce more and more different applications. That's why the functionalization itself is really a broad area where we were working. I was even working functionalization of carbon nanostructures using organic molecules. Here they have used DNA as a functionalization source for carbon nanotubes. They grow gold nanoseeds. Because of the fluorescence effect, they get enhanced luminescence of fluorescence. Here they used for some blood cells, or like here it is named, FA labeled KB cells. So these cells are imaged using carbon nanotube effect using fluorescence microscopy. The carbon nanotube have advantages over getting into like different level of penetration. So it gets all the information from everywhere without any boundary restriction. So that's why they're using nanotubes. As a microscopist, I see like scanning electron microscopes and transmission electron microscope, which clearly shows how the nanotubes are bundled with DNA and gold nanoseeds have developed over it. So another example of NIR imaging using carbon nanotubes, they just try to capture video images in a mouse and pointed out different regions using the imaging. Like they injected uh, polyethylene glycolated single wall nanotubes, because single wall nanotube have more uh, fluorescence effect also within this NIR2 boundary regions from 900 to 1200 wavelength window. So that's a second window compared to the primary window, which is 400 to 700 nanometer. So it's more helpful in getting NIR2 imaging window here using carbon nanotubes. That's mostly with single wall carbon nanotube. So they used nano towards biological applications. But there are different imaging applications using Raman or fluorescence or photoacoustic. Of course, I'm not good in photoacoustic imaging tumors. So I'm not. I just brought it how this carbon nanotubes used in different applications. I'm not good in explaining these things. Of course, they are used in PET imaging. For example, they deliver a drug using carbon nanotubes that get into the PET imaging later on. So nano and bio and interdisciplinary, these are my papers which I want to show you, like just 4 papers which I was used as a material science or published as a material scientist, helping the biological people or biomedical people getting published using by electron microscopy knowledge. So I just provide them electron microscopy image. For example, this paper is published in CIT, PhD student Gayatri. She used magnesium incorporated hydroxyapatite. I just helped her in imaging these things using advanced electron microscopy. And this is a collaborative paper from Pondicherry University where they have zinc selenide and zinc sulfur core shell nanorods. Selenide is in core and sulfur is in shell. So I was working in China where I was working in electron microscopy group where we have ChemiSTEM technology, advanced electron microscopy where we can even get EDS mapping for such a very small 10 nanometer or 5 nanometer scale of nanorods or nanoparticles. So I have used my knowledge to provide a solution or bring insight into what these nanorods contain, whether it is core shell or just ordinary nanorods using ChemiSTEM EDS mapping. Then they have used it for bioimaging later on for HEK 293 and HELA shells. So these things which we work together from material science to the bioimaging. And this is another paper we published together with Swansea University where they used waste tea leaves as biosurfactant in synthesis cadmium sulfide quantum dots. They used it for, they studied the cytotoxicity effect in breast cancer cells. I have used my TM knowledge to get this image and get the quantum dots mapped here, which is around 5 nanometer. Then they used it for, of course, they used for bio application later on. My part is end here with electron microscopy knowledge. This is another paper which I'm working with SRM University. Its manuscript work is finished and it's submitted to some journal where they have zinc oxide and silicon dioxide core shell nano structures. They loaded with curcumin as like a drug delivery system, and they have also used for bioimaging. So curcumin loaded core shell zinc oxide, silicon dioxide nanostructures for bio applications, but this image shows only core shell, zinc oxide, and silicon dioxide. So I have used, it's my image. I have used electron microscopy for them to get this image for further research work. They've used it for different biological applications. Maybe they publish one by one with different applications later on. So these are the things we work closely and interdisciplinary in nature, irrespective of where we are. So there's a broad opportunity for as a material scientist, as I can say. And coming back to the international collaboration possibilities and direction, yes, I tell you an example. When I was working in China, every Chinese department, every Chinese professor have linked to the like international universities through a Chinese. So it means it's no matter where the Chinese professors or researchers are working in this world, but they are again connected to their own university or partner universities in China provide international knowledge to the Chinese students. So it's like I felt the Chinese are very best example of getting the international network through their own Chinese people. I cannot say the Indians are not good in that, but I can say Chinese are every Chinese have their such a mentality. Who are going outside of China, getting back to their own country and getting into the more collaboration. So I was really amazed by how they are structured mentally or prepared mentally to come back to their come back to their homeland or associated by somehow. And I can say every department have their own international collaboration. Every department have every professor have international collaboration. If you see Chinese paper, whether it is published in Nature or any other top journals, you see 5 different universities, but everyone come from China, like Chinese people, Chinese origin. So this is the mentality we should develop as an Indian. Of course, we are ready for open, like into coming back to India or giving more of our international knowledge to our Indian students to get into more international collaborations. Of course, you might have seen few papers. That's why I wanted to bring those papers. When I was even doing PhD in Norway, I brought University of Bergen in close collaboration with University of Coimbatore Institute of Technology, because I just bridged them. Now it's like 7 years of fantastic research work was going on. Every PhD student in physics department of CIT is getting chance for 3 months of Norway research, coming to Norway and do research. Like within their PhD framework or within their PhD period, they at least they come for 4 or 5 times. Such a broad possibilities are opened up. Of course, I was one among them who made a bridge. Even when I was in China, I just made a MOU with Chinese University, with CIT. We are working towards that. Of course, I want more international Indian researchers should come forward to make such possibilities. Even we have recently submitted few collaborative research papers and even collaborative project proposals in IIT Spark, which is very good starting point, I can say. As you might have known, at least senior professors might have known about that IIT Spark collaborations for getting fund for Indian research to do in foreign land or foreign universities. So that's a one like opening. But there are, of course, there are more international project collaboration proposals are coming in every year, every month. There are more Indo-Sweden collaboration papers, project proposals or calls are coming in using DST and Swedish research, and I see there are more Norwegian and Indian project funds are circulating everywhere around Indian universities. It's a good sign of development, but we need to develop more. Of course, I'm open in like giving a direction or show my experience how to do or how to approach these things. I'm more open in even not only in this talk. You can even approach me later on. We can at least see. I don't know. I cannot promise you whether we can collaborate together, but at least I can show you or explain my experience how to do this. So with this, even I'm open for questions now regarding this. If you have more questions related to this, we are really happy to answer you, and we can have more discussion over it. With this, I'm thank you for your kind attention. Really, I'm open to answer any question.
Okay. Thank you, Professor. It was a wonderful presentation, and you're looking for collaborations. It's really nice. And this is time for questions. If you have any questions, kindly post in a chat box. Otherwise, you can ask the questions here. If you have any questions, kindly unmute your microphone and then speak. If you are facing any trouble, kindly post your question in a chat box so that we can ask the question to Professor. He can answer.
Hello, Vijay.
Yeah, hi.
Yeah, hello. It's not a question. Actually, I've been associated with you a long time. I feel very happy to be hearing the presentation. It was a highly physics, chemistry, and biology perspective, along with the machine learning perspective also. It was a nice presentation. It was a nice, what are the various collaborative perspective on the Indian student project. We will try in level best in future. We'll do some collaboration along with your ideas. Thanks for your highly motivated presentation. I know personally you are highly committed with various research works, and recently you published some good papers. I seen you in the FB. Not only in research, social work also you are doing some good thing during the COVID-19 crisis. Along in your busy schedule, you give some time for our department for giving guest lecture. It was highly informative to us. Thanks for your good presentation.
Yeah, thank you, Nias. Thank you.
Hello.
Yeah, சொல்லுங்க. Hello. Sound கொஞ்சம் disturbance. There was some disturbance.
Hello.
Yeah, கொஞ்சம் TV sound குறைச்சுக்கோங்க. Like
Hello, sir.
Yeah, சொல்லுங்க.
Hello.
மேம் உங்களோட அந்த பேக்ரவுண்ட் நாய்ஸை வந்து கொஞ்சம் கம்மி பண்ணிட்டு பேசுனீங்கன்னா நல்லா இருக்கும் மேம். பேக்ரவுண்ட் ஆடியோ ஏதோ ப்ளே ஆயிட்டு இருக்கு, அதை கொஞ்சம் கம்மி பண்ணிட்டு பேசுங்க.
Hello.
சொல்லுங்க, எனக்கு கேக்குது, கிளியரா இருக்கு, நீங்க சொல்லுங்க, பேசுங்க.
Okay. So this is Gomati from Interdisciplinary College. Yeah. So thank you so much, sir, for your wonderful and motivated presentation, and also your immediate acceptance. And on behalf of the management and also the Department of Biochemistry, once again I thank you, sir.
Yeah.
Hello.
Yeah.
Good afternoon, sir. This is Srinandini from Kaidamilat Government College, Chennai.
Yeah.
Sir, I'm basically from a zoology person. So, being a zoology person, how can I have a collaborative project with the physics department, sir? In what aspects I can have a collaborative project?
No, any collaboration starts from the like department to department approach.
Okay.
I can give you first general thing, then you can proceed with more specific question and answer. We can have communication later on.
Okay, sir.
How we started like CIT and University of Bergen is we started with like MOU within the department of like in physics department of University of Bergen, because every department in foreign university have the chance to get MOU with any universities or any department around the world. So we started MOU with physics department of University of Bergen and CIT. Then later published few papers together, because for any international calls they ask whether you have already worked together or at least a similar platform. So interdisciplinary way, for example, you are in zoology and if you want to collaborate with physics department, at least those department research works and your department research work should be published together before getting into the inter call get selected, I can say. That's my experience at least.
Okay, sir.
Succeeded for last 6 years with CIT and University of Bergen. So start with MOU or start with collaborative research papers, then get into more in-depth research work. We can even have separate discussion.
Okay, sir. Thank you so much, sir. Thank you. Thanks, sir.
Hello.
Yeah.
So this is Gomati again from Interdisciplinary College.
Yeah,
So,
please.
is the interdisciplinary projects or research are appreciable nowadays?
Sorry, I'm not hearing you clearly. Please repeat the question.
Is the interdisciplinary projects or research works are appreciable one?
Yes,
Accepted
yes.
one nowadays?
Yeah. That's very much.
But most of the people are demotivated like this interdisciplinary courseworks
No. Actually,
project work.
I'm actually a victim of that because I was from a material science. Like I studied applied science, which is a triple major, and material science. I got degree from Indian university approved universities, but I cannot come now because of these policies. Because they need academic professor should be like BSc physics or PhD physics or chemistry. But I'm more interdisciplinary in the international research environment. Now, even to come back for me, it's a problem. I have very limited options like in IIT. Of course, I understand the situation. Like this interdisciplinary is academically not like, at least for us, it's not a completely acceptable in AICT norms. But as a research person, you can still have wide opportunity. No one is stopping you to collaborate or publish or get research fund in a different field of work once you are settled into like in some university as a professor. Yeah.
Okay. Thank you, sir. Thank you.
Hello.
Yeah, please.
Hello. Hello.
Yeah, please.
Sir, good evening, sir. Hello.
Yeah, சொல்லுங்க எனக்கு கேக்குது. Yes.
Hello, good evening, sir. This is Aruna.
Actually, voice break ஆயிடுச்சு.
Hello.
Yeah, voice
Hello.
break. But please, at least try to post your question so at least I can answer you if it is having some network issues.
Now also you're having problems, sir. Now I think it is
Yeah.
clear.
Please continue now. Yeah.
Sir, thank you for your presentation. It is really nice, useful presentation. I'm Aruna from Excellent College. I would like to invite you for our association or any seminar, sir. If it is possible to attend, sir.
Yeah, of course, it's an open platform you're asking, but of course we can discuss it. Just as it is for the general audience, please just raise questions alone. For these questions, of course, we have separate communication, I can say. Sure, I'm accepting
Okay,
it.
sir.
Let's discuss it directly.
Sorry. Okay, sir. Will you give some more information about nanoscience related to biotechnology, sir? Just a few things.
No, means,
Hello. Sorry for the interference.
Hello.
Yeah, Niyaz sir, சொல்லுங்க.
Aruna ma'am, I will give his details. You will utilize him, his expertise.
Okay, sir. Thank you.
Okay. Vijay, you go ahead, please.
Yeah. Actually, nanotechnology in பொறுத்தவரையில it's we are talking, right? Like as I said, if I take only alone carbon nanotubes, the carbon nanomaterial itself, it's more interdisciplinary and you can use it in all applications. Even I showed few slides on how nanorods are used in bioimaging. So it's like nano core shell particles are used in cancer therapy. Even in carbon nanotubes are used in cancer therapy. It has a wide opportunity. So it's very broad question. So I pick a straight line from here, but I don't know. There are more papers which published like combine nanomaterial into the biological and medical applications, we can say.
Okay.
I can answer only general because it's very broad. Sorry.
Okay, sir. Thank you.
Vijay, நீங்க PPT மோட்ல இருந்து வீடியோ மோட் வந்துறீங்களா?
Yeah, sure.
Any more questions from the fellow participant?
But still, நீங்க என்ன questionsனால இல்ல என்னோட மெயில்ல நீங்க தொடர்பு கொள்ளலாம். You can write me a mail. Yeah.
Ananthalakshmi ma'am.
I think she's having some problem.
Pamadi ma'am.
Sir?
I think she is
Sir,
having
yes,
some
sir?
problem.
Yes, sir. Yes,
Yeah,
sir.
வாங்க மேம்.
Yes, sir. Hello. Yes, sir.
ப்ரொசீட் பண்ணுங்க, கேக்குது.
Hello, any questions from the participants?
Yeah, I see there are many chat box with just complimentary words. Thanks for that. Thanks for your really good presentation, like attendance even in May 1 Labour's Day. I wish you all good luck. Of course, I'm open for any kind of discussion or communication through email, or even I can just write my email here. You can always contact me, and I will also give my mobile phone. You can contact me through WhatsApp, whichever is convenient. So hopefully everyone must have received through my chat box, right? Yeah.
Vijay sir, I think we can wind up.
Yeah, okay. Anyway, I have provided my mobile and mail ID, so you can always contact me.
Yeah.
For you, or I am here for our people. I am here for our students. So don't hesitate. I'm more open in this. Yeah.
Okay. Thank you, sir. Thank you, Vijay sir. And it was nice presentation and good attendance we have. A live streaming ID வந்து எல்லாருக்கும் ஷேர் பண்ணியிருக்கேன். At the same time, I will share the live streaming ID and feedback form through mail. Kindly send your feedback form, as well as you can, if you have missed anything, you can watch through live streaming URL. And if you have any questions, also you can post through mail. Okay, I think this is a nice time to wind up.
Thank you.
Okay.
Thank you very much.
Thank you all.
I thank Open Space Foundation and Sacred Heart College for providing such opportunity. Thank you very much. I'm leaving. Thank you.
Thank you,
sir.
Anandal. Thank you.
Thank you, sir.